Good evening and welcome to this video for the 2017 Level 3 Complex Numbers exam paper for Level 3 Calculus. So question 1, if u equals to 2 plus 3i and v equals to 1 minus 4i, find the conjugate of u minus 3v, giving a solution in the form a plus bi. So we know that u equals to 2 plus 3i, therefore the conjugate of u must be equal to 2 minus 3i. We know that v equals to 1 minus 4i. So therefore, the conjugate of u minus 3v equals to 2 minus 3i minus 3 times of 1 minus 4i. In this case, if we expand our brackets, we should get 2 minus 3i minus 3 plus of 12i. And in this case, we can just add these terms like terms, so the imaginary parts go together and the real parts go together. So the real parts are 2 and negative 3. 2 minus 3 equals to negative 1. And we know that negative 3i plus 12i equals to positive 9i. So this becomes negative 1 plus 9i, which is our final answer. And this is just an achieve level question. So achieve for getting your correct final answer. Question B, write 36 over 5 minus square root of 7 in the form a plus b root of 7 where a and b are integers. So in order to rationalize the denominator, we need to multiply by the conjugate. So in this case, we have 36 over 5 minus root 7. So we need to multiply the top and the bottom because we're multiplying by 1. So we need to multiply the top and the bottom by 5 plus of root 7. So multiply both the top and the bottom by 5 plus of root 7. So this is the same as multiplying by 1, so we're not changing the question. So in this case, we have 36 times of 5 plus 36 times of root 7 all over 25 minus 7. So in this case, we have 36 times of 5, which is equal to 180 plus 36 root 7 all over 25 minus 7, which is 18. So in this case, 180 over 18 is 10, so this becomes 10. 36 root 7 over 18 becomes 2 root 7, so this becomes 10 plus 2 root 7, which is our final answer, and this is just another achievable question. Question C, solve the following equation for x in terms of p. So we have p square root of x minus 2 minus 5 root of x equals to 0. So in these types of questions, we have two square roots. So we're going to two terms of square roots in it. So in this case, we're going to separate the square roots so that we can get rid of both square roots just by squaring both sides. If we square the result right now, then we're going to be left with more square roots that we have to deal with, which makes the problem a lot harder. So in this case, we're going to say that p square root of x minus 2 equals to 5 root of x, and now we're going to square both sides. So p squared times of x minus 2 equals to 25 times of x. So therefore, p squared of x minus 2 equals to 25x. And the question asks for x in terms of p, so therefore it should be x equals to something something. So we have to make x a subject, so we're going to expand the left-hand side here. So we have p squared of x minus 2p squared equals to 25x. And we're going to group the like terms, so we're going to move the 25x to the other side, it becomes negative 25x, and we're going to move negative 2p squared to the other side, becoming positive 2p squared. So p squared x minus 25x equals to 2p squared. By doing this, we can now factor out the x as a common term on the left-hand side. So factoring out x, we get p squared minus 25. That equals to 2p squared. And now we can divide both sides by p squared minus 25. So x equals to 2p squared all over p squared minus 25. And that is our final answer for this question. And this is a merit level question for getting the correct final answer. And the achieved criteria is correct expression without surds. I assume that they mean by correct expression without surds. So I assume that no surds means that you got rid of all the square roots successfully. So I'm just assuming that if you can just square both sides, then that should be enough for an achieved actually. So if you can get up to here, that's an achieved. D, one solution of the equation z cubed minus 2z squared plus bz minus 30 equals 0. And one solution to that cubic equation is negative 2 minus I. If b is a real number, find the value of b and the other two solutions of the equation. So by the conjugate root theory, we know that if negative 2 minus I is a solution, we know that the conjugate of that must also be a solution. So basically, by conjugate root theorem, I'm just going to abbreviate to conjugate root theorem. So by conjugate root theorem, if z is a solution, that means the conjugate of z must also be a solution. So therefore, one solution is z equals to negative 2 minus I, which means that another solution must be negative 2 plus of I. So those are our two imaginary solutions, and there's going to be one more solution, which is going to be a real solution. So in this case, we're going to write out our brackets. We have z minus negative 2 minus I, and we have we have multiplied by z minus negative 2 plus of I, and we're going to have some z plus of c, which we're going to try to find out, and that equals to our cubic z cubed minus 2z squared plus bz minus 30. Alright, so now we're going to expand these brackets. So now we have z plus 2 plus I multiplied by z plus 2 minus I times of z plus of c, which equals to everything on the right hand side. So now we can actually expand these brackets. So when we expand, we know that one of these solutions is the conjugate of the other, which means that we can ignore all the imaginary terms. So when we expand this, we can ignore all the imaginary terms. It's only going to be real terms, and the reason for that is because we're multiplying by the conjugate, and if we multiply by the conjugate, all the imaginary terms will actually cancel out. So you can write out the imaginary terms, but if you write out the imaginary terms, then at the end you'll find that all of them will cancel each other out, and you'll only be left with the real terms. Okay, so in this case we have z squared multiplied by 2 times z plus 2z. Z times of negative I is negative zi, but it's an imaginary term, so we just don't have to worry about that. Now we have 2 times of z, so plus 2z again. 2 times 2 is 4, so plus of 4. Plus 2 times of negative I is negative 2i, that's an imaginary term. So now we have z times of I, that's positive zi, that's an imaginary term. Plus 2i, that's also an imaginary term, so don't worry about that. So I times negative I is negative I squared, which comes plus of 1. And that's multiplied by z plus of c. So if we simplify this, we have z squared plus 4z plus of 5 multiplied by z plus of c. Alright, so now we're going to expand with this third bracket. Okay, so z cubed plus cz squared plus 4z squared plus 4cz plus 5z plus of 5c, and that equals to that cubic equation. So that equals to z cubed minus 2z squared plus bz minus 30. And we know that 5c equals to negative 30 because that's the only term that's independent of z. That's the only term that does not have z in it. So therefore we know that 5 times of c equals to negative 30. Therefore c equals to negative 6. Using c equals to negative 6, we can actually substitute c equals to negative 6 into our cubic, and we can find the values of value of b. So in this case, we'll have z cubed. So c is negative 6, so it becomes negative 6z squared plus 4z squared plus 4cz. 4 times of c is negative 24, so that becomes negative 24z plus 5z minus 30. And you find that this simplifies to z squared minus 2z squared minus 19z minus 30. And now we can clearly see that b equals to negative 19. And in the third solution, we know c equals to negative 6. Therefore, the third solution is equal to 6 because it's xz, because we have this. So z squared plus 4z plus of 5 times of z minus 6. So therefore, z equals to 6 is a solution. Alright, so that's all we really need. So we just need to state all our findings. So we know that negative 2 minus I, negative 2 plus of I, and 6 are solutions. And we know that b equals to negative 19. Alright, so that's all we need for this question, and this is a merit level question. If you can find b equals to negative 19 and the other two solutions found correctly will get you a merit. To get an achieved, you need either b equals to negative 19 or z equals to 6. So basically, if you can get b equals to negative 19, or you can find the third solution, you'll get an achieved. So either of them will get you an achieved. Question E, find the Cartesian equation of the locus described by the modulus of z plus 2 minus 7i equals 2 times the modulus of z minus 10 plus of 2i. So for these types of questions, you always define what z is. So z is going to be a complex number. We'll just say that z equals to some a plus bi. So we just say let z equal to a plus bi. So now we're going to have a plus bi plus 2 minus 7i equals to 2 times the modulus of a plus bi minus 10 plus 2I. So now we know that imaginary terms will go with imaginary terms and real terms will go with real terms. So in this case, we're going to group our real terms, so that's a plus of 2. And we're going to group our imaginary terms, which is b and bi and negative 7i. So plus b minus 7 times of I, that equals to 2. We're going to do the same thing on the right hand side here. So a minus 10 plus of b plus of 2i. Alright, so now the modulus is basically, if I draw the Argand diagram here, for example, we have this complex number z. The modulus is basically in simple terms, is the distance from the origin to that complex number. So this distance here, that would be the modulus of z. So to find the modulus of z, okay, we have our imaginary part of z here and our real part of z here. So by the Pythagorean theorem, we know that the imaginary part of z squared plus the real part of z squared, that equals to a modulus of z squared. So in order to find the modulus of z squared, we just take the square root on both sides. So imaginary part of z squared plus real part of z squared. So we're going to do the exact same thing here. So we know for the left hand side, we know that a plus 2 is the real term, b minus 7 is the imaginary term. And for the right hand side, we know that a minus 10 is the real term and b plus 2 is the imaginary term. So now we can just use that to find our modulus. So in this case, we have a plus of 2 squared plus b minus 7 squared square root. That equals to 2 times the square root of a minus 10 squared plus b plus of 2 squared. So now we're going to square both sides. So now we have a plus 2 squared plus b minus 7 squared. That equals to 4. Don't forget this 2 at the front. When we square it, 2 times 2 is 4. So don't forget, very common mistake. So when we square it, we're squaring this whole thing here. So 2 times 2 is 4. So 4 times of a minus 10 squared plus of b plus of 2 squared. Alright, so now we're going to expand our brackets. So a plus 2 squared becomes a squared plus 4a plus of 4. B minus 7 squared becomes b squared minus 14b plus 49. And that equals to 4 times of a minus 10 squared becomes a squared minus 20a plus 100. B plus of 2 squared becomes b squared plus 4b plus 4. Alright, so now we're going to simplify this a bit further. So the left hand side will stay the same for now. So minus 14b plus 49. That equals to 4 times of everything inside the bracket. So that's 4a squared minus 80a plus 400 plus 4b squared plus 16b plus 16. Alright, so now we're going to move everything to one side and make equal to 0. So 0 equals 2. So we have 4a squared on the right hand side, a squared on the left hand side becomes 3a squared. And that similarly becomes 3b squared because we have 4b squared on the right hand side and b squared on the left hand side. Alright, so we have positive 4a on the left hand side. So we're going to take away 4a, we move it to the right hand side. So minus 80a minus 4a. So minus 4 plus 14b minus 49. And plus 400 plus 4b squared plus 16b plus 16. Alright, so now we just need to group our like terms. Okay, so 3a squared plus 3b squared minus 84a plus 30b. And we have negative 53. Sorry. Plus 363. Right, that seems right. So 3a squared plus 3b squared minus 84a plus 30b plus 363. Let me just double check that. Yep, that seems right. Okay, so now in order to write it in our Cartesian form, so we want it to be in the form x plus a squared plus y plus b squared equals to k. That's actually a locus that represents a circle, okay? So in order to do this, okay, so first we're going to make our a squared and b squared coefficients equal to 1. Since they're both equal to 3, we can just divide everything in our equation by 3, and that's going to leave us with the coefficient of 1 for a squared and b squared. So 0 equals to a squared plus b squared. We can divide we have to divide everything by 3, because what you do to one part of the equation, you must do to the entire part of the equation in order to keep it true. So 0, obviously, on the left-hand side, we have 0. 0 divided by 3, that's still 0, so we can just leave it as that. So negative 84a, we're going to divide that by 3, and we're going to get negative 28a. 30b becomes 10b, and 363 becomes 121. Right, so the next step here is we're going to move the 121 to the other side. So we have negative 121 equals to a squared plus b squared minus 28a plus 10b. So now our next step is to complete the square. Okay, so we're going to be completing the square. So in order to complete the square, we need to write it in the form that was expressed above there. So that's x plus a squared plus y plus b squared equals to k. Alright, so in order to do that, we're going to say negative 121 equals to a, and we're going to take the half of the negative 28, which is negative 14 squared plus b plus of 5 squared. Alright, so notice that once we put it into this form, that's a minus 14 squared plus b plus 5 squared, we're going to get, if we expand these again, we're going to get a squared minus 28a plus 14 squared. And for the b plus 5 squared, we're going to get plus b squared plus 10b plus 25. As we can see here, the a squared and the negative 28a is found here. And the b squared and the 10b are found here. However, we're adding in 14 squared and we're adding in 5 squared. So by adding in the 14 squared and the 5 squared to one side of the equation, we must also do it to the other side of the equation in order to keep it true. Since we're adding in this 14 squared and 25 on the right hand side, we need to add 14 squared and 5 squared on the left hand side in order to make it true. So we're going to end up with an equation that represents the 14 squared is 196 plus 25 is 221, sorry. And if we take away 121, we'll get 100. So a minus 14 squared plus b plus of 5 squared equals to 100. And you can just leave your answer like that, but if you want to be a bit more specific, you can say that the circle has a center of 14, negative 5, and we can say that the radius equals to 5. That's not 5. Radius equals the square root of 100, which is 10. Alright, so that's our final answer for this question, okay? And if you can get up to your final answer, so that's correct Cartesian equation, you'll get an excellence grade. To get a merit grade, you need a correct equation for x and y without i's or surds. Okay. So if you can get up to this part here by squaring both sides, you'll have, if you can square both sides, you'll have a merit grade. To get an achieved grade, you're correctly separating the real and complex components on both sides of the equation. Alright, so I assume what they mean is that if you can get up to this step here, so writing out this modulus here, you'll get an achieved. Alright, so question 2. Dividing x cubed minus 2x squared plus 5x plus d by x minus 3 gives a remainder of 13. Find the value of d. So in this case, we know that if x cubed minus 2x squared plus 5x plus of d is divided by this x minus 3, it gives a remainder of 13. So basically, what this is saying is that if we have x minus 3 times of some function q of x plus of 13, that's going to give us to our original equation x cubed minus 2x squared plus 5x plus of d. Qx can be anything because it's just dividing x cubed minus 2x squared plus 5x plus d by x minus 3. That's going to give us this q of x, doesn't matter what it is. So notice that if we put x equals to 3 into this equation, then we'll get back to this remainder of 13. So therefore, if we say that p of x equals to x cubed minus 2x squared plus 5x plus of d, therefore p of 3 must be equal to 13. So in that case, we can just substitute and we can find out our d value. So therefore, 13 equals to x cubed, 3 cubed, minus 2 times of 3 squared plus 5 times of 3 plus of d. 3 cubed is 27 minus 2 times of 9, which is 18, plus of 15 equals to 24. So 13 minus 24 equals to d, and therefore d should come out to be negative 11. So d should come out to be negative 11, and that is our final answer for an achieved grade. Question B, simplify as far as possible the expression the square root of 2k times 18, square root of 18k minus square root of 8k. So once we have a square root multiplied by a square root, it's the same as saying the square root of everything inside multiplied together. So in this case, we have, if we expand these brackets, we'll have square root of 18k times of 2k minus square root of 8k times of 2k. So this simplifies to square root of 36k squared minus square root of 16k squared, and these are perfect squares. So 36k squared square roots, that becomes 6k minus 4k, and this simplifies to just 2k there, and this should just be an achievable question. Question C, z and w are complex numbers such as z equals to negative 2 plus 3i and z times w equals to 15 minus 3i. Find an exact value of the argument of w. Okay, so we know that z times w equals to 15 minus 3i, and we know z equals to negative 2 plus of 3i. So therefore, negative 2 plus 3i times of sum w equals to 15 minus 3i. So therefore, w equals to 15 minus 3i divided by negative 2 plus 3i. And in this case here, we're going to be multiplying by the conjugate in order to evenly distinguish our imaginary part of our w and the real part of w. So we're going to multiply by the conjugate, which is negative 2 minus 3i, by the top and the bottom, so you just multiply by 1. So in this case, we should get negative 30 minus 45i plus 6i plus 9i squared, which is negative 9, all divided by, so negative 2 times negative 2 is 4, 3i times negative 3i is negative 9i squared, that's positive 9, so 9 plus 4 is 13. So w equals to negative 39 minus 39i over 13, and this equals to 3 minus 3i, negative 3 minus 3i. Right, so when you're finding the arguments, so I always recommend that you can draw out the Argand diagram. So if we draw out the Argand diagram, just a rough sketch, doesn't have to be perfect. That's not very neat, but just a rough sketch, doesn't have to be perfect. So negative 3 minus 3i, we can clearly see that should be somewhere here. So that's our w, and our argument will simply be the angle. Here, that will be the argument. Right, and we know that this length is 3 and this length is 3. So basically, we can find this angle theta by using our Pythagoras theorem. So basically, that's just saying that tan of theta equals to 3 over 3. So therefore, tan theta equals to 1. Theta equals to tan inverse of 1. And you should get that theta equals to pi over 4. However, that you might say that pi over 4 must be the final answer. However, that's not correct because we're trying to find the argument, and the argument is basically defined as the angle from this line here. Okay, so basically in this case we know that this angle is pi over 4. We know that a full revolution equals to 2 pi, and we know that this angle we can clearly find by using pi minus pi over 4. So pi minus pi over 4, that gives us 3 pi over 4. And when we talk about complex numbers, we know that going anti-clockwise is positive and going clockwise is so going anti-clockwise is positive and going clockwise is negative. So in this case, we're going to say that the argument of w equals to negative 3 pi over 4. Alright, and that should be our final answer. Okay, so argument of w is negative 3 pi over 4, and that should give us a merit grade. To get an achieved grade, you have a correct expression for w. So getting w equals to negative 3 minus 3i is an achieved. Question D, solve the equation z to the power 4 equals to m over root 2 plus m over root 2 times of I, where m is real and positive. Okay, so m is real and positive. So write your solutions in polar form in terms of m. Right, so once again, like I just did in the last question, we're going to draw out the Argand diagram and locate this point. So we know that m is real and it's positive, so m is greater than 0. So therefore, if m is greater than 0, then m over square root of 2 must also be greater than 0. So we know that both the imaginary part and the real part must both be greater than 0, and they're equal in magnitude. So in this case, we're going to find that our z to the power 4 should be somewhere there. So this will be our z to the power 4, and this here will be our complex number, which is the real part is going to be m over root 2, and the imaginary part will also be m over root 2. we can actually find this angle here by using our Pythagoras once again. So tan theta equals to m over root 2 divided by m over root 2. So therefore tan theta equals to 1. So theta, once again, that equals to pi over 4. But this time it's positive, since if we're starting from this line here, we're going anti-clockwise, we should find that the argument equals to pi over 4. So therefore, if we write this in polar form, so therefore z to the power 4 equals to the modulus of z to the power 4 cis of pi over 4. To find the modulus of m over square root of 2 plus m over square root of 2i, we can just use the Pythagoras theorem once again. So we know that the modulus is distance from the origin. So therefore, m over root 2 squared plus m over root 2 squared. And if we take the square root of the whole thing, we'll get the modulus of z. So m over root 2 squared equals to m squared over 2. So therefore, this becomes m squared over 2 plus m squared over 2. And therefore, m squared over 2 plus m squared over 2, that's just m squared. So this simplifies to m. So what we have here is z to the power 4 equals to m cis of pi over 4. Alright, so now we're going to be finding our solutions to this equation. And first of all, we're going to take the fourth root of both sides. So therefore, z to the power 4 equals to m cis of pi over 4. So therefore, z equals to the fourth root of m. Cis of, and the angle gets divided by 4. So pi over 4 divided by 4 is pi over 16. Alright, so since we have z to the power 4, so if the power is 4, therefore that tells us that there's 4 solutions to this equation, just 4 solutions. Therefore, for example, if it's 3, z to the power 3, then there's 3 solutions, z to the power 5, there's 5 solutions, z to the power 6, there will be 6 solutions, etc. And in this case, that means for each complex number, it's going to be an angle of 2 pi over 4 away from each other in terms of radians, because one full revolution around the axis is 2 pi. And if we go around once in the circle to the same place, it's the exact same complex number, it's the exact same solution. So for example, saying cis of 0 is the same as saying cis of 2 pi, since it's saying the exact same point on the arcane diagram. That's a similar thing with this case here. If we're going around the circle and ending up in the same place, that's just going to give us the exact same complex number. So in this case, we know that there's 4 solutions evenly spaced around 2 pi radians. That means that each complex number must be 2 pi over 4 radians away from each other. So therefore, to get our next solution, we'll simply just add 2 pi over 4 to our current argument. Okay, so therefore z2 equals to the fourth root of m cis of pi over 16 plus 2 pi over 4. And alright, so this should give us z2 equals to the fourth root of m cis of 9 pi over 16. So therefore z3 equals to fourth root of m cis of 9 pi over 16 plus pi over 2. Pi over 2 is the same as 2 pi over 4. So z for the third root is 4 root of m cis of 17 pi over 16. And the fourth root would therefore be 4 root of m cis of 25 pi over 16. Sorry, 25 pi over 16. Right, that's our final answer for this question, okay? You can choose to, for the 17 pi over 16 and 25 pi over 16, since it's greater than pi, so therefore it will be on somewhere around this side of the axis. Therefore, you can actually convert it to negative. But since in NCEA it's optional, okay, so conventionally you would change it to a negative. However, since it's NCEA, they don't mind. You can just leave your answer in the positive, and that will be fine as well. So this getting your final answer will get you a merit question. To get an achieved question, you only need 1 correct solution. So 1 correct solution will get you an achieved. Or you can have 4 correct arguments. 4 correct arguments will get you an achieved. Alright, so question E. Find all possible values of k that make u equals to k plus 4i over 1 plus ki a purely real number. So a purely real number means that the imaginary part of u must be equal to 0. So basically, imaginary part of this u must be equal to 0. So first thing first, we have 1 plus ki on the bottom there is a complex denominator. Therefore, we're going to multiply by the conjugate in order to see our imaginary part of u and our real part of u more clearly. So u equals to k plus, sorry, it's a bit messy. So u equals to k plus 4i over 1 plus ki times of 1 minus ki times of 1 minus ki, because we're multiplying by 1, not changing the question, not changing the u. So in this case, we're going to have k minus k squared of I, sorry, that's 4i, plus 4i plus 4k all over 1 plus k squared. So now we're going to group our imaginary terms and our, sorry, that's k squared. Okay, so, sorry, it's not k squared, k times, okay, yeah, sorry, I apologize. Okay, so now we're going to group our imaginary parts and our real parts together. So the imaginary part of u is simply just k plus 4k, since that's the real parts. So therefore, we have 5k over 1 plus k squared, plus of the imaginary part, which is negative k squared I plus 4i. So plus negative k squared plus 4 over 1 plus k squared times of I. So to make it a purely real number, we know that the imaginary part of u must be equal to 0. So therefore, negative k squared plus 4 over 1 plus k squared must be equal to 0. Therefore, negative k squared plus 4 equals to 0. Therefore, k squared equals to 4, and therefore k equals to plus or minus 2. Alright, and that's actually our final answer for this question. Okay, so not a pretty simple excellence question if I'm being honest right now. Okay, so that's all it took to get an excellence. K equals to plus or minus 2 will get you an excellence grade. To get a merit grade, you need negative 4k squared over 1 plus k squared equals to 0. So basically, getting up to this step here will get you a merit. To get an achieved, you need a correct expression for u rational denominator. So if you can get up to here, you'll get an achieved. Alright, so okay, I'm actually going to leave question 3 for another video because it's getting a bit late. So it's going to be in a separate video. So I hope you enjoyed watching this video, and I hope to see you on the next one. Thank you.